Have a good break. You might have a bad break. Did you not? What did you do over break? Huh? Oh. Yeah, some of you guys work. But this is my work, so I literally get a week off. And I come in and say, how was your break? And I'm like, I worked all week. Wasn't anything. Usually after a break, I feel like we had a week, and I come back and I'm like, man, that didn't seem like a week, you know? But this time, I feel like it was 2 weeks ago. It's so weird. I feel like I had 2 weeks off instead of 1 week. I can't explain it. All right, I'm gonna review chapter 4. No, chapter 5. So I've done chapter 4. We just ended chapter 5 before we left for break, so it's chapter 5 I'll review. I wanted chapter 4, 5, and 6 to be on this next test, but there's no way we're gonna go all the way through chapter 6. So we'll do part of chapter 6, and whatever of chapter 6 we're gonna do, I'll do Thursday of this week. Then we'll have next Tuesday as a review, and then next Thursday will be test 2. That quiz, definitely not gonna do it this week or next week. I'm not gonna do it the following Tuesday after the test. So I still feel like it's more than 2 weeks out. I mean, I wanna be able to go over information from test 1 that'll be on the quiz, and then I want you to have time with that to be ready. So just worry about test 2 right now, and I'll give you time to go back for test 1. All right. And what I'm about to review is essentially drawn. So these quizzes from chapter 5, stuff we use. So a couple of examples, representative examples of each thing. So, how many C atoms are in 4.41 moles of atoms? 4.41 moles, that has a unit. How many C atoms? It doesn't say how many grams, it doesn't say how many moles, it doesn't say how many milliliters, there's no unit. So that means you're going to use this relationship. Because there's no unit. So the lack of the unit is what's canceling. And of course you're going to use it no unit, like this, or flipped over. So for this one, start with what it gives you. 4.41 moles of carbon atoms. From there, moles is on bottom, from 1 mole, or let me do this with labels. Carbon atoms, and then 1 mole carbon atoms. No unit. Carbon atoms. So the moles cancel, you end up with no unit there. That's how you'd solve that question. 4.41 times 6.02. My calculator says, and then I'm just going to tack the 10 to the 23 there. If you wanted it in scientific notation, it would be this is correct if you're not asked for scientific notation. That's if you, standard scientific notation. How many, I might as well fix this before I upload. Almost the same question, but same type of question, but you have to do this. Now it's not just carbon atoms. Oh no, I don't have to do that. We're still doing, okay, never mind, this will be quick. 0.63 moles of H2SO4. It's 10 to the 23rd. .63 times 6.02. My calculator says we're keeping two significant figures because of this. That's showing 3. So I have to do 3.8. And it's already in standard scientific notation. You guys okay? All right. The next type of questions, you're told how many and you're asked for moles. So instead of just a number over here without a unit, I should have done this. Just to keep the labels consistent. It's 2 S's, 4 molecules. All right. This next one is asking you for moles, not how many. How many moles of AL2O3? So you start with this. 10 to 23. No unit here. So on the bottom is where you're going to put the 6.02. AL2O3. In my calculator, I'm just going to divide 1.59 divided by 6.02. I'll do this. And then I've got 10 to the 23. 10 to the 23, those are just going to cancel. So that 10 to the 23, that 10 to the 23. The blank and blank will cancel, so I'm going to be in moles of AL2O3. All right, so those are just going to cancel, and I'll get 1.59 divided by 6.02. 3 significant figures. Those will cancel. And if you were asked for scientific notation, it would be standard scientific notation. So that's correct, but if you're asked for standard scientific notation, it would be this. Similar, how many moles of H2 molecules are in? Oh, I didn't change that number. I haven't uploaded it yet. Let me just, how many moles you want it to be? 2.57. Times 10 to the 21. And here I only have to change the label. Now, H2, moles of H2. On the bottom I have 21. No. If I move this to the top, times 10 to the 23, I make it negative 23. And then 21 minus 23 is 2. So 10 to the negative 2. So I'm here, so now 2.57 divided by 6.2. 3 significant figures, so I'm going to go my calculator said 0.426910299. I'm keeping 3 significant figures. The 9 rounds the 6 to a 7. This is correct, but if you were asked for standard scientific notation, it would be 4.27. Negative 1, 2. If I want this to be in scientific notation, I need to move the decimal 1 place. Ten to the 1, we'll move it up here, but I'm also going to do 10 to the negative 1 because that equals 1 and that doesn't change the value. And now I'm going to perform that operation and that operation. 10 to the 1, so I did do that wrong. Two 7 times 10 to the 1 times 10 to the negative 1. This still seems wrong. What am I doing wrong, y'all? 10 to the negative 2. I want to multiply it by 10 to the 1, 10 to the negative 1. So that makes 4.27, that does. This makes it 10 to the negative 3. Oh yeah, okay, that's right, that's right. This is, if I move this 2 places, 1, 2, that's really what the number is, 0.00427. So that's right. I knew I did it wrong, so I had to do my algebra trick. And I still got confused. All right. So these big numbers, the definition of a mole is used here for A and B, and then the big numbers show up here, plus the definition of a mole. But here we get past those huge numbers with 10 to the powers of 10.
So we won't be using 1 mole equals 6.02 times 10 to the 23rd in any more of these. No more of these questions will that huge number show up. Now the definition we're going to need is, what is the mass in grams of 4.14 moles of NH3? It mentions moles and it mentions grams and it mentions NH3. So think to yourself, you're going to need the grams per mole for NH3. Nitrogen, there's 1 of them. Hydrogen, there's 3 of them. And just to remind you, you look here for nitrogen, 14.01. Hydrogen is 1.01. 3.03. You add them up. And you stick a G per mole. That's the grams per mole for NH3, also known as ammonia. 4.14 moles is what we're told. Moles needs to go on bottom. I tell you guys, when you have this type of symbolism, the number goes on top with this, and then what's on bottom gets a 1 in moles. So you want to use it that way. Or maybe you're going to use it flipped over, but in this case we can use it like that because moles needs to be on the bottom. So it's essentially 17.04 times 4.14. That's what my calculator says. I'm keeping 3 significant figures, so that's moles cancels, and we end up in grams. That's the answer. Scientific notation. Scientific notation is really only useful for those huge numbers. In chemistry classes and science classes, at least introductory, they act like we do everything in scientific notation, but we don't. Any chemist is going to leave that the way it is. It doesn't serve to put that in. So another one of this type, another question of this type. For CO2, carbon, we've got some carbon there, we've got some oxygen there, we have 1 carbon, 2 oxygens. Carbon is 12.01 on the periodic table. The periodic table we use, the one I handed out to y'all and that we use on the test, says 16.00. That oxygen over there probably says 15.998 or something. We'll stick to 2 digits after the decimal here. $13. 44.01 grams per mole. So we're going to need that. We have 233 moles of CO2. 44.01 grams CO2, 1 mole of CO2. Mole goes on the bottom. So this is going to be a lot of grams. So 44.01 times 433. I'm pretty sure I meant to put 2.33. Let's do that, just add a decimal. Just stick a decimal right there. Still gonna be huge. 2.33 times 44.01. Calculator says 102.5433. We're keeping three significant figures, so it's just that. So 103, moles cancels, grams of CO2. 103 grams of CO2. No reason to change that to scientific notation. Okay. Stepping up the difficulty ladder just a little. How many moles is 23.6 grams of this? So now we're being asked for moles and we're being given grams. We still have to calculate. 3 carbon. Carbon, we have 3. Hydrogen, we have 8. Oxygen, we have 2. 12.01 off the periodic table. 1.01. 16. 36.03. 8.08. And 32. I think I did that right. 8, 9, 10. $76.10. I'm gonna double check that. So we're going to need that, and we're going to take our C3. We have our grams per mole here. We want grams on the bottom, so we're going to use it like this, 1 mole. And now we're going to end up in moles. Let's see, 3H8O2. Calculator says 0.310118265444. 4 significant figures 3, so we're keeping these 3, so it's 0.310. And the next one, Al2O3. Um, 22.99. Is that right? no, I did 26.9. 26.9. Six, nine, 5, 8. $85.96 grams. How many grams is it?
Can you put it on color screen?
I am. 14.14. It's gonna give us moles. How many moles in Al2O3? Calculator says and we're keeping 4 significant figures this time. This 9 will round to 4, so it's 0.1645.
Up there with the O, it says 3 times 16 is 32. That
Oh. Oh, what is it? 41.
48.
So 101.96. Now my calculator says keeping these 4, the 8 rounds to 6. No more mistakes. Now we kick it up one more notch. And we actually look at a reaction. Hopefully that looks a little familiar because we did cover ionic compounds. But I'm not going to throw naming back at you. But this is saying how many moles of this are produced when you use this many moles of this. I went ahead and calculated the grams per mole ahead of time, and I'll probably do that on the test. And you're not going to need all of those. I just did them all before I made up the question. How many moles? So we're going to have equals some number moles of SNI2, 10 iodide, and we start with 1.12. We have this many moles of SN. 1.12 moles. So we have that in moles. The next thing we need is the molar relationship between this and this. Maybe just run 2 eyes. Well, I guess it's fine, but this molar relationship is kind of null, but 1 mole of balance. Yeah, it's balanced, so mole of so how many moles of S and I are produced from? You don't need the grams per mole for this one. And of course, this is just gonna end up being I thought I wrote these to where I at least had different digits, top and bottom. That's why I keep thinking I put a mistake in there. NO32 is balanced. No? Yeah, I did, okay. The next one will be a little more interesting. Yeah. So this was going from moles to moles, and all we needed there was this molar relationship between the tin nitrate and the tin iodide. I want this open. Is it on? That's why I'm getting a little. This one, 6 Na and 2, okay. This one, notice it's going from moles to moles again. It's saying if I put in, okay, if I produce 0.450 moles Na2SO4, how many moles of Na are needed? So the moles of Na2SO4 is 2 moles to 6 moles of Na. And you could just reduce this to 3 and multiply it, but I usually just leave them since I'm gonna do it on my calculator anyway. 0.450 times 6 divided by 2. So 1.35 moles of sodium will be needed to produce 0.450 moles of Na2SO4. You with me? Okay, these are still kind of simple. That just showed you how to use the equation to get the molar relationships. So you didn't need any of this. I think the next one, okay, how many grams of Ki are needed to produce 4.41 grams of tin iodide? So now we're going to have to deal in grams. It says how many grams of Ki. So I'm going to do this on this side of the equal sign. How many grams of Ki? What we're given is 4.41 grams of tin iodide. We we need the grams per mole of the tin iodide, so that once we get beyond there, we're in moles. Tin iodide, 372.52. So if you pulled out the periodic table and you found out the number for tin and you multiply the number for iodide times 2, added them together, you would get 372.52 grams per mole. Next, we need moles of tin iodide on the bottom. And we're relating this to Ki. Grams to grams, so yeah, I need more space. So it's 2 Ki to 1 mole tin iodide. You see where I'm getting these numbers? That's gonna put us in moles of Ki, but we wanna be in grams of Ki. 166 grams per mole. 0 grams of Ki is 1 mole. Now we can calculate it. I'm just curious if I'm still.
Glass cabinet is a black box about this
I've
high.
got plenty of space. That's terrible though. Need to write bigger. Anybody calculate this? 4.41 times 2 times 166 divided by 372.52. Three significant figures is what we'll use. .93 grams of K. I might need to write bigger. Since we calculated the amount of grams of one of the products, you can call what we just calculated the theoretical yield. This is asked in theory. If I put 4.41 grams of this reactant, no. How many grams of Ki are needed to produce? Yeah. So to produce this, so no, that's wrong. That's not theoretical. Since we calculated the amount of the reactant, that's not a theoretical yield. It's just worth pointing out that it's theoretical yield when it's a product, because it will help when we get to percent yield. Okay, this one. How many grams of Na2SO4 are produced? Okay, and that's a product. So now what we're calculating is actually theoretically yield. And it helps to know that when we do the next thing down, percent yield. And I've got to write bigger.
much sleep last night, I'm feeling it now. Alright. So, equals, calculating how many grams. -2, that's 4. And we're gonna start 14.61 grams. SO4. Two. SO4. Yeah. Should have opened that door. Too late now. Alright. This is what we're given. We need grams. Put that down here. Run out of space again. We need the grams per mole for Al2SO3. 342.16 is 1 mole. All right, and now we need that on the bottom and Na2SO4 on top. Equals, I'm afraid I'm running off the camera here. All right. So now we need, so what's the ratio? 1 of these, 2 of these, and then we need the grams per mole. Na2SO4, which is 142.2. Fourteen, 6.1 times 2 times 142.02 divided by 342.16. Calculator says, I'm going to use 4 significant figures here. That's exact, that's exact, that's exact, that's exact. 4 significant figures, 5 there. So my calculator says, keeping those, the 8 will round the 2. You guys follow that? And that one was a theoretical yield because we were calculating the amount of a product.
So where did you get the 2 for the 2 moles of Na2SO4? Just from the second one.
Na2SO, that too? Is that what you're asking?
Like, and when you worked it out, is that where you got the 2 from? Was the second part of the
Yeah.
Okay.
This 2 is from here, and the 1 is here. You get that? And these are grams per moles. So this is the molar relationship from the equation, grams per mole, grams per mole. And this was the given arbitrary thing.
this next one, this one's actually simple. It's just to remind you how you calculate percent yield. And I noted that theoretical yield is what we've been calculating. And it's always that gives you percent. I.e. So you put actual over theoretical, and this is that long walk calculation that we've been doing, or at least in the very last problem. Actual, that's always given. It's arbitrary. It's usually less than the theoretical yield because you lose a little bit sometimes, or most of the time when you're doing reactions. And that's why we have percent yield, just to sort of tell you how good your lab process is to make whatever product you're making. So this one, if the percent yield is and what does it give us? It says the theoretical yield is 9.55. Theoretical. I'll say, no, I shouldn't say X. I'll say question mark grams. And then you just solve with algebra. Divide both sides by 100. It's going to give you 0.85. The percent cancels. These grams cancel too. So I'll just simplify it to however you want to do this algebraically. I think I would there's a quick way to get there. No. Multiply both sides by 9.55. So that leaves us with question mark. And now just multiply those together. .85 times 9.55. Calculator says this, but I'm keeping, what am I keeping? The percent counts the significant figures, so I've got to have two significant figures. So what I'm looking for here is so really you just have to remember that formula and then just do algebra from there. And notice you can be given actual and percent and asked to calculate theoretical. You can be given theoretical and percent and asked to calculate actual. You can be given actual and theoretical and asked to calculate percent yield. There's three variables in that question. As long as you get 2 out of 3, you can solve the third one. Okay. Now the finale. We'll have 2 more. So notice here, if 3.98 moles of sodium reacts with 1.25 grams of Na2SO4, reacts and Na2SO4, 1.25 grams of Na2SO4 was produced, what is the percent yield? So it's implied here that 1.25 grams was the actual yield. Saying that's actually what happened. We got 1.25 grams from this. So the 1.25 grams is the actual yield. Can you see that? And you wouldn't be getting a percent yield question unless there was an actual yield involved. So what you have to do first is what we did earlier. You have to calculate what is the theoretical yield of Na2SO4. Then you'll have your theoretical yield and your actual yield, and then you can calculate percent. You follow that? So we do like we did before. .98 moles of Na reacts. We need moles of Na on bottom. And we go straight to moles of Na2SO4. Six moles of Na, 2 moles of Na2SO4. Now we need moles of Na2SO4 on bottom, grams on top. And that'll give us the grams of Na2SO4 that 3.98 should theoretically create. What am I missing? Gotta fill in the grams. 142.02. So that'll give us our theoretical yield. I just think it helps to keep in mind that the theoretical yield is the long one to calculate. The actual yield is just given. .98 times 2 times 142.02 divided by 6. Three significant figures. Calculator says 188.4132. We're keeping 3, so it's just the 188 that we're keeping. Grams. The actual yield. Did I do 3.98? Yeah. If the actual yield was 121.25, it's going to be incredibly small. I'm pretty sure. I should have done 125. Sorry. I'm going to upload this, so if you're sitting there taking notes, you really only need to take these notes. But let's do that just so it's not ridiculous. So, actual over theoretical. 125. Theoretically, we should have gotten 188. I should have grams here. The label is Na2SO4 on the top and the bottom. I guess I'll stay consistent. Na2SO4. And we should get this fraction here. Times 100. This will be 3 significant figures. calculator says 66.48936170.
Now, aluminum.
Keeping 3, the 8 will round the 4, so 66.5 percent. That's the percent yield. So just remember, when we've got a percent yield question, what's given as the product is the actual yield. And if it's not given, then they're gonna give you, if they don't give the actual yield, then you're gonna need the theoretical yield, and they'll give you the percent, and then you can find the actual yield. But you'd still have to calculate the theoretical yield. This is an easy one. If 16.1 grams of Ki are used in the reaction, and 17.2 grams SNI2 are produced, so what do you do here? Oh no, we do have to calculate the theoretical. Okay. Okay. Here's what's used in the reaction, 16.1 grams of Ki. Potassium iodide. We're gonna need grams of Ki on the bottom. That's gonna be the grams per mole. This. This is the wrong set. Ki is 166.00. That's 5 significant figures. All right, next, we're gonna need moles of Ki on the bottom. And this is where we're gonna switch over to SNI2. SNI2 is being produced, and it is 1:1. Now 2 Ki, 2 Ki to 1. Now we want mole of SNI2 on the bottom. Grams are 372.52. $16.1 times 37252. Divided by 166, divided by 2. 5 significant figures there, 5, 3 there. 18.1 grams of methanol. But we're not done. That's our theoretical yield. This one scales. So using the reaction, it's 17.2 grams are produced. That's the actual yield. What do we get here? Calculator says keeping 3 significant figures. The 9, 5, and the 0. Grams cancel, grams cancel. We're like 1%. 3 significant figures, 9, 5, and 0. Yeah, y'all remind me to open that door next time. All right. That's all of those. Hopefully I fixed all the mistakes in it. I want to introduce you to one thing from chapter 6. And there's a fair amount of stuff in this chapter, but these types of calculations are so similar that I'm just jumping straight blind into a different concept. I think you'll appreciate seeing how to calculate this before you see all the other stuff that goes in this chapter. So I told you before, when you've got a chemical equation, such as, this will look familiar. 2Ki. I'm just curious if this is still going. Still going. So those two reactants, and then you come. And I told you that there are 6 relationships here. Remember me saying this? And in all these problems I've been doing, for any given problem, I really only needed one relationship. But it's the relationships are 2 moles of Ki to 1 mole. There's one of the relationships. So it's that relationship. Here's another relationship, these two. 2 Ki, 2 moles. Always stick moles in there. 2 moles of Ki to 1 mole SnI2. And you can build all of them, and any one of them you can use whichever way you need it. This way or flip it. All right. What I want to show you about this is there's always an amount of energy that either goes into a reaction or is released from a reaction. So sometimes a reaction will release energy, pretty much always heat, at least in any examples we would use. So picture pouring 2 things together, holding the beaker and feeling it get real hot as soon as you pour them together. Or you could alternatively pour two things together and it feels cold. Sometimes they produce heat and sometimes they absorb heat. And really, the only other thing to say before I show you this is, the energy unit we'll use is the calorie. Frequently done as kilocalories. I think I need to keep that lowercase. So unit of energy, I won't say any more about it today, but six, I might get through one of these. Let's do 6.26, and I'm just going to write that equation down. It's 2NH3 and that's just, so that one molecule splits apart into 3 H2s and 1 nitrogen. I'm also leaving off, this means it's a gas, the G here means that's a gas. The N, they just omitted it, they should have put something there. It's really a partial reaction, but it won't matter. 2. I'm not going to make y'all do balancing. That needs a 2 there. There's 2 of those, and there's 6 hydrogens. 6 hydrogens, 2. You know what? This is what they left off. Yeah. There should be an N2 there, and we almost certainly meant to put a G in parentheses with it as well. But okay, so just pay attention to what I got on the board. I've got practice problems for you to do in the quizzes, so. How much energy is absorbed? Okay. This is the thing to tell you, 22.0 kilocalories. We call this delta H. That letter won't mean anything to you, but it's just kind of what we call this. So when you do this reaction, the way it's written, it's 22.0 kilocalories. And what that means is if 2 moles of NH3 reacted, it would release 22.0 kilocalories. But there's 2 more relationships here. So I've got this 3 from here, and I'm just literally using the same number. I'm not pairing these now, I'm really pairing each one of these just with kilocalories. Those are the 3 relationships related to energy for this reaction. You're just literally just grabbing this like you did before, turn it into moles, and whatever the delta H is, you write up here. And now the first question is, how much energy is absorbed when 1 mole of N2 is formed? Don't look at that N, I mean this. And the one we want to use, of course, is this one. And we want moles on the bottom. The moles cancel. Of course, here we're just going to get 22.0. But what if it said 4.64 moles of N2 was produced? How much heat was produced when this was produced? You do it just like this. See what I'm saying? They can also ask, they use the word produced if they're talking about these 2. In this question it says reacts when it's talking about the reactant. But let's do this one with grams. What if